Carbohydrates are well known as a food entity, but they're also very important in other parts of biology. The name carbohydrate comes from the empirical formula of all of the simple carbohydrates was found to be carbon, 2 hydrogens, and 1 oxygen. And to the early scientists, this looks like it was carbon that had been hydrated. You can see water attached to a carbon. So they called these molecules carbohydrates. We're going to look at the structure of them and really try to understand how they're put together and how they, from there, you can use this information to see how they fit into biochemistry. Simple carbohydrates are all going to have an ose ending on the end. So you hear glucose, you hear mannose, you hear ribose. Those are all the simple carbohydrates. Of the carbohydrates, there are monosaccharides, disaccharides, oligosaccharides, polysaccharides, and then there's complex carbohydrates that are complex with other types of molecules. Monosaccharides are they're essentially just one sugar unit. Disaccharides are 2 sugar units that have been condensed together. They're joined together with the loss of water. Oligosaccharides are several of them. And then polysaccharides are many units that are all stuck together. And when they're stuck together, it's all by a condensation reaction that you'll see later on. All of these are water soluble except for polysaccharides, which are water suspendable usually, but they are not soluble. As I already stated, the empirical formula for all of the monosaccharides is 2 hydrogens to 1 carbon and 1 oxygen. We classify them based on the number of carbons, triose, tetrose. Notice it's tetra, not bute for 4, and it's tri, not prop for 3. But then it reverts to our standard pent, hex, and hept, and oct. So we classify them based on the number of carbons. Notice it's the number followed by ose. All of the monosaccharides have either an aldehyde or a ketone functional group. So there's 1 carbonyl group on every monosaccharide, and if it's either the aldehyde or the ketone. If it's an aldehyde, we call it an aldose. If it's a ketone, we call it a ketose. And then every single carbon that is in that molecule is going to have a hydroxyl group attached to it. So every carbon has an oxygen attached. It's just one of them has an oxygen attached by a double bond. The rest are single alcohol groups. So here's an example of some monosaccharides. This is an aldotriose. We combine the descriptions. So aldose for an aldehyde, ketose for a ketone. This is an aldehyde group, so this is an aldotriose because there's 3 carbons. Notice a hydroxyl group on every carbon that doesn't have the carbonyl on it. This is a ketone, so we call this a ketohexose. Notice there's 6 carbons. Every single carbon has an oxygen on it, all of them alcohols except for the one that is a ketone. This simple triose right here, the most simple monosaccharide that we have, is called glyceraldehyde. And so it's an aldehyde, and then it has 2 alcohol groups on it, of course, because it needs to have an alcohol group on the remaining carbons. This is fructose right here, and we'll go into figuring out how you can recognize it being fructose later on. Other sugars will have the same look right here. Fructose has a specific stereochemistry, and there are other ketohexoses that have the same structure but have a different stereochemistry than fructose. So this really is a very generic drawing of a monosaccharide right here. So go ahead and classify this monosaccharide and then draw a tetrose that's also an aldose. Okay, we see that this has 5 carbons and it's a ketone, so this is a keto pentose, a ketose that is a pentose. And for us to have a tetrose that's also an aldose, let's put an aldehyde on it, then 4 carbons, 1, 2, 3, 4. Every single carbon has an alcohol group on it. And if we want to shorten this name and make it more compact, we call it an aldotetrose. Now D and L stand for dextrorotary and levorotary. We identify both our amino acids and our carbohydrates by D and L, but it actually has nothing to do with the way that light is rotated. It does if you are dealing with chemistry, but not in biochemistry. And it's based on a configuration of the carbon. So we're going to go into this in greater detail so you better understand. D and L in chemistry stand for dextrorotary and levorotary, but when we get to biochemistry, it takes off in a different direction. All of the monosaccharides are written in Fischer projections or Haworth projections. The Fischer projections, you know, you're going to see the skeleton lying down and then the things across. And you remember that the sides that are parallel to the ground are coming out at you, and the line going up and down is going back, bending backwards. So keep that in mind when we look at these Fischer projections. And then we'll also look at Haworth projections. So where do D and L come from? D and L comes from dextrorotary and levorotary. And if I look at the dextrorotary glyceraldehyde, it has this structure. And if I look at the levorotary glyceraldehyde, it has this structure. All of the monosaccharides are based on looking at these two structures. And it doesn't matter which way they rotate light, even though these two rotate to the right and to the left. After this, you don't care which way it rotates. We're just looking at the configuration of a particular carbon. So keep that in mind. So this is L-glyceraldehyde and D-glyceraldehyde. The D-glyceraldehyde is the one that occurs in nature. L-glyceraldehyde is synthesized by chemists in the laboratory. If I take D-glyceraldehyde and convert it to a Fischer projection, remember what you do is you twist it so that you have the two that are parallel to the ground coming out at you, and then the ones that are up and down are going back. And so this structure can be converted to this Fischer projection right there. So in all of our monosaccharides, we put our carbonyl closest to the top, and everything else hangs down. Remember that every carbon has to have an alcohol group on it if it doesn't have the carbonyl. So carbonyl, alcohol, alcohol. This is D-glyceraldehyde. In D-glyceraldehyde, when we put it in the Fischer projection with the carbonyl at the top, the hydroxyl group is on the right. For all D carbohydrates, what you do is you draw your Fischer projection so that the carbonyl is closest to the top, and then you look at the bottommost chiral carbon. It's going to be the second one from the bottom. And if the hydroxyl is on the right, then it's a D monosaccharide. That's all we look at. Has nothing to do with rotation of light once you get past D-glyceraldehyde. So here's D-glyceraldehyde. There's L-glyceraldehyde in the Fischer projections. Let's look at some other carbohydrates. Okay, of course, this is something important. The numbering always starts at the carbon at the end that's closest to the carbonyl. So this is 1, this is 2, this is 3. Keep that in mind when we're looking at these carbohydrates. Okay, now let's look at this. This right here is glucose. The carbonyl is at the top. Glucose is an aldohexose. So you will see 1, 2, 3, 4, 5, 6 carbons. A hydrogen's missing here. There should be a hydrogen written here, like over here. If I look at this, you can see when we draw glucose, D-glucose, the hydroxyl groups are going to be right, left, right, right. Notice I wrote RLRR. It's an aldose, so we have a carbonyl at the top, right, left, right, right. How do I know this is D-glucose? I look at the bottommost chiral carbon. The bottommost chiral carbon is the second one from the bottom on every single monosaccharide. So I go down here, 1, 2. Notice the hydroxyl group is on the right. So this is D-glucose. Now, another name for D-glucose is dextrose. And this does confuse people because they think glucose is different from dextrose. And when we say glucose, it has to be D-glucose because all of the natural monosaccharides are all D sugars. So D-glucose and dextrose are the same thing. And if we just say glucose, we're always talking about D-glucose because L-glucose is only made in the lab and it's very expensive to make. These are how the carbons are numbered, 1 with the carbonyl and then going down. Fructose is just like glucose. It is identical to glucose, except that it is a ketose rather than an aldose. If we had glucose here, this would be a carbonyl, and then we would have a hydroxyl that was right, left, right, right. Well, when we convert glucose to fructose, we slide the carbonyl down here, and this right-handed hydroxyl group now becomes a carbonyl. And of course, the carbonyl now becomes a hydroxyl group. You can see that fructose has exactly the same structure as glucose, except for the carbonyl being moved down. Ribose is an aldopentose. And if I look at ribose, aldehyde, and notice all of the hydroxyl groups are on the right. These three structures, glucose, fructose, and ribose, are very easy to remember, and they're the most common sugars that you will encounter in biochemistry. So it won't hurt for you to sit down and try to draw these a couple of times so you can remember them. Notice D, fructose. Why? The second hydroxyl from the bottom, the chiral one, the first chiral one, is on the right. On the right. So these are both D sugars. And of course, there's the numbering. Okay, here is ribose. What about deoxyribose? With deoxyribose, it is just ribose with a hydroxyl group removed. And so it's the first one from the top that is removed and turned into a hydrogen. And that's why it's called D and A, because it's made with deoxyribose sugar. So really the riboses are identical in RNA and DNA, except for this one hydroxyl group, which is fascinating how that gives it such